We're going to talk about conditional probability. Before we do, I just want to kind of look at some of the probability topics and which ones are most likely to be involved in a problem based on its sample size. If you're only selecting one thing, then we're looking at basic probability and whether we have independence between two events, using the addition rule, and the word "and" will mean intersection. So simple probabilities there. If we select two or three things, we're likely looking at the multiplication rule. We have to decide whether we're selecting with replacement or without replacement. The word "and" means multiplication. And now when we get to size 2 and 3 samples, we could very well be looking at joint distributions. I'll put together a video on that. And then there can also be linear transformations for a sample size of 1, and ugly conditional probabilities. They go down here too, which is what we're about to discuss in a moment. But then as we go to bigger and bigger sample sizes, you get a problem with a sample size of somewhere between 3 and 15. There's a pretty good chance that we're looking at a binomial problem. If we have a sample size 4 to big, could be sample means if it's asking you, hey, what's probably that the mean is whatever. And then if we have really big sample sizes, there's a pretty good chance we're dealing with sample proportions or successes which are binomial that could be converted to sample proportions. So that's pretty much the picture based on the sample size. Again, in probability, my opinion, the sample size is one of the first things you want to look at when you're dealing with probability. So we're going to deal with the conditional probability. Here's our formula right here. And I'm going to take a little license here, and there could very well be some people that disagree with me, and you may or may not like the approach that I take with these problems because of what I'm about to say. But I'm going to read this as A and B, and not as A intersect B. And the reason for that is I'm going to decide later, based on the way we approach a problem, if the sample size is 1, then "and" means intersection. We're going to go ahead and find the intersection of two things. But if the sample size is 2, that's a 2 actually down there, then this can mean multiply. Now a big problem that I've even seen good teachers do this, they just accidentally fall into it. A lot of people will automatically multiply stuff up here. That's bad news. That's usually going to lead to a problem, but not always. So that's why I say if we could read this as and then in reading the problem decide, well, are we only selecting one thing, and should "and" mean intersectional? Let's find the intersection. Or can we better describe the problem or look at it from the standpoint that two things are being selected, and then the word "and" will mean multiply. So hopefully as we go through this video, you'll see what I mean, and then it's up to you or to your instructor as to whether you agree or disagree with this approach. But so let's proceed. Suppose we have this Venn diagram, and we're asked to find the probability of A given that B has occurred. We can follow the formula, and a Venn diagram implies that only one thing was selected, so the probability of A and B occurring is in the intersection of A and B. It would be that 0.2. So we'd say, okay, this is equal to 0.2, and then we divide it by the probability of B, and B, the set B, is made up of these two regions, so altogether that would be 0.6. So we'd get 0.2 divided by 0.6, and we'd have our formula right there. I teach my students to shrink the sample space down. A lot of times that's easier to do a problem like this instead of going through the probability formula, and it really does the same thing. So another way to look at this would be to say, hey, what's the probability of A happening given that B has occurred? Well, if B has definitely occurred, then we can rule out these two situations right here, and we're just down to that 60%, that 0.6 right here. And out of that 0.6, how much of it is in event A? The 0.2. So I'll teach my students to shrink the sample space based on the given information down to, in this case, just event B happening. And out of the 0.6 that's in event B, only 0.2 of it is also in A. So again, we get the same probability. This is a helpful approach when it comes to something like this. Let's say we have female students and male students that are in taking AP classes, either no AP or one AP class or 2 or more APs. Sorry guys, the gals are tending to outperform us in the real world. But anyway, let's suppose this is the data that we've collected, and we want to find the probability that we've selected a male given that the person we've selected has 2 or more AP classes. So the quickest way to do this problem is just shrink the sample space. We're given that the person selected has 2 or more AP classes, so we can eliminate all those people because we're given that it's down to just these people with 2 or more AP classes. And out of those people, which that totals up to 60, out of those 60 people, 25 of them are males, so this probability would be 25 out of 60. If you don't like the shrink the sample space approach, then you could still follow the formula. The formula says find the intersection of the two. Where do you find a situation where you have both males and they've had 2 or more AP classes? Well, it's those 25. So that's the intersection of those two levels. And then divide it by the probability that someone had 2 or more AP classes. That would be those 60 people. But honestly, if you did that, we really would have to do it this way. We'd have to consider, if you follow the formula, that there's a total of 210 people. There's 110 females and there is 100 males for a total of 210. So if you follow the formula, you'd have to say, okay, let's find the intersection of males, and what's probably that we find somebody in the intersection of they're a male and they have 2 or more AP exams. That would be 25 people out of 210, because the formula says find the probability of them being in that intersection. So it would be 25 out of the 210. We would divide that by the probability of the thing that was given. What's given here is that the person had 2 or more AP courses, so that would be 60 people out of 210. So if you were going to be a purist and follow the formula, it's the probability of a male and a person with 2 or more AP classes, which is 25 out of 210, divided by this. When you divide those guys out, then the denominators cancel and you get 25 out of 60. So you want to be versatile. You'd like to be able to do it both ways, using the formula and shrinking the sample space. But I think it's hard to argue with the fact that if you just shrink the sample space down to what you're told occurred, which in this situation was a person had 2 or more AP classes, then you're just down to these 60 people right here. And the probability you get a male out of that is 25 out of 60. So in my opinion, whenever you can shrink the sample space and do it more concisely that way, I think you're better off. So now let's suppose we're going to roll 2 regular 6-sided dice. We want to find the probability that the sum is 8, given that a 3 was rolled. Well, we can follow the formula here again. It's the probability the sum of 8 given a 3 was rolled. So we want to find the probability that we get a sum of 8 and a 3 was rolled. So now if we're going to follow the formula, then there are 36 outcomes when you roll 2 dice. 6 times 6, 36 outcomes. So in the numerator, the probability that you get a sum of 8 and a 3 was rolled is, well, let's see, out of the 36 outcomes, how many of them give you a sum of 8 and at the same time a 3 was rolled? That would be this guy here and this guy here. So there would be 2 out of 36 chance that you would randomly roll 2 dice, get a sum of 8, and have a 3 involved among the 2 rolls. Now you're going to divide that by the probability that a 3 was rolled, and if you look at that, then you're going through and you're going to say, okay, in all these situations, where will a 3 be rolled? Well, it would be these 6 situations right here, and these 6 situations right here where a 3 was rolled, but this one was counted twice, so altogether there would really be 11 distinct rolls in which one of the numbers, at least one of the numbers, was a 3, so that would be a probability of 11 out of 36. So if you're going to follow the formula, the probability that you get a sum of 8 out of 3 was rolled, that's 2 out of the 36. Boom, boom. And then you divide that by the total probability that a 3 was rolled. That's 11 of the outcomes out of 36. So that's how you'll get your probability. You could reciprocate and multiply. One way or another, the 36s are going to cancel. And your final probability would be 2 out of 11. Now once again, I would argue for the idea that if you are going to the lattice diagram, you can see all the information you have. So I would argue that, okay, the sum of 8, given that a 3 was rolled, let's shrink the sample space down from the 36 outcomes we have initially, just down to the 11 outcomes where there was a 3 rolled. And out of those 11 outcomes in which at least one 3 was rolled, there are 2 of those in that resulting sample space for which the sum is 8. So our probability would be 2 out of 11. So it's a lot quicker to shrink the sample space. Let's see how quick this is. I think if you try this problem, try this one. What's the probability that you rolled a 2 given that the sum of the 2 dice was a 5? So if you rolled 2 dice, what's the probability that you roll at least one 2 given that the sum on the 2 dice was 5? Well, if you look to the lattice diagram, can you shrink the sample space down to what was given, that the sum was 5? Well, you get a sum of 5 here with a 1 and a 4, here with a 2 and a 3, here with a 3 and a 2, and here with a 4 and a 1. And out of those 4 things that could happen where you get a sum of 5, this one and this one involve rolling a 2, so your final probability is 2 out of 4. You shrunk the sample space down to the 4 scenarios where the sum is 5. Given that the sum is 5, those 4 situations, what's probably a 2 was rolled? A 2 would be rolled in this case and in this case. By the way, when I have my students look at have you guys look at a lattice diagram, then you could think of it as one of the die was red and the other die was green, so that you can see the 36 outcomes better that way. Hopefully that makes sense. I'm an advocate for shrinking the sample space whenever you can, but certainly just be comfortable with following the formula. Now this next example is going to give an example of when it might be good to read the word "and" as 2 things happening, and so we'll multiply. And it's the biggest beast of all the conditional probabilities. It's these problems that are like the disease problems. So let's suppose that 3% of people living along a certain canal have the lobes of their ears fall off. But don't worry, they get replaced by beautifully colored ones a few weeks later. But let's suppose there's a dude in the area that collects these ears. He lives in a van, and he goes by the name Julius Caesar because he's a Roman citizen. He lives in a van, he's a Roman citizen, and he's always asking people, hey, lend me your ears, so that he can make some beautiful artwork with them. So it's kind of funny when he drives by in his van, they say, hey, look at that van go. But anyways, that's the whole ear thing. It's goofy. Let's move on. I'm embarrassed. We have a blood test that can be given to detect the condition. It gives a positive result for 98% of people with the disease and a positive result for 4% of the people without the disease. So it can give a false positive. So if we randomly select a person who tested positive, find the probability that he or she does not have the disease. Whew. So that's one of those ugly deals right there. Now, here's where I would say in years of teaching this, the thing that early on I discovered was the way that most kids could grasp onto this, especially the ones that are maybe the more marginal students and probably doesn't come as easy to them. I'm going to ask that we consider that 2 things are happening. A person's either got the disease or not, and then a person's taking a blood test. So I'm going to say in these disease problems, let's consider that 2 things are occurring. Therefore, the word "and" is going to mean multiply, and therefore the way to describe this might be best shown with a tree diagram and not a Venn or anything else. So again, here's our information. 3% of people have the disease, 98% test positive, 97% don't have the disease, 4% of them test positive. Trying to find the problem that they don't have the disease, knowing that the person tested positive, and there's our formula. Well, if we go to the tree diagram, then the first thing that has to happen is we have to really consider the fact that a person has the disease or they do not have the disease, because their testing positive or not is going to depend on whether they have the disease. Because there's got to be 2 places on the tree diagram to put down the 2 different values for testing positive. That's what tells us that testing positive is dependent on whether they have the disease or not. So if we write the tree diagram like this, we can weight the edges that there's 3% that have the disease and 97% that don't, that 98% of the people with the disease will test positive, 2% won't, and then 4% of the people without the disease will test positive, and 96% won't. So then if we go down here and we say, okay, here's our strategy for finding this conditional probability, and this is where I'm saying let's consider this to be the word and. We want to look at people who do not have the disease and they test positive. So if we look at it as two things, they have the disease or not, and they do a blood test, then we can justify a tree diagram. We can say and means multiply. So we're going to say in the denominator, we're going to follow the people who do not have the disease. I guess I'll use black marker. They do not have the disease and they test positive. So if we take this times this, we're going to get 0.0388. Okay, so that goes in the numerator, 0.0388. That, of course, is a 3. We're going to divide that by the probability that somebody tests positive. And again, we can rephrase using the words and or. Where do people test positive? They can have the disease and test positive, or they cannot have the disease and test positive. So if we multiply these guys together, we get 0.0294. So the total probability of testing positive is it can be disease and positive, boop, or add to this times this. So it's going to be, this is going to get us our result. If we take this divided by the total probability that somebody tests positive, that's our conditional probability. I wrote it down 0.5689. So this total conditional probability is 0.5689. And once again, we can shrink the sample space. We can draw the tree diagram. We can say we know the person tested positive, so we can eliminate this outcome from our sample space and this outcome from our sample space because those people tested negative. So the population, the sample space, shrinks down to just these people here, this 2.9% and this 3.9% roughly. So out of that total sample space that's left, what's the probability that they don't have the disease? That would be these people out of the sample space that's left. So hopefully this helps. Those, you can expect a problem like that almost every year on an AP Stat exam, and these are the tougher ones, I think, in regards to conditional probability. So good luck with that. And again, you may or may not, there are other very good instructors out there that would argue with me that this is not the way to teach it, to interpret that as being and to make the tree diagram. It's just my personal opinion that this has been the way that's made the most sense to everybody. So get with your instructor or tutor or whatever. If there's another approach to this, certainly you could look at that and then decide, hey, which one makes the most sense to me. So anyway, good luck with conditional probability.